Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. Today, I'm going to continue with eigenvalues and eigenvectors, and I'm going to take two more examples, one in 2D or a 2 by 2 matrix, I should say, and one for a 3 by 3 matrix. So, the first example I want to work is I have a matrix A, and this matrix is basically um, pi over 3, negative pi over 3, negative 2 pi over 3, and positive pi over 3, or 2 pi over 3. And this matrix, I want to find its cosine. Okay. So how do we find the cosine of the matrix? It's the same idea. We are going to find the eigenvalues and eigenvectors and write matrix A as P, D, P inverse, and then take the cosine of D and then multiply them back. Okay, so it's the same process, so to speak. So let's see how we can find the eigenvalues. We are going to do again lambda I minus A, determinant of that and equate it to 0. So let's work this out. So now I have pi over 3 minus lambda, negative pi over 3, negative 2 pi over 3, and 2 pi over 3 minus lambda, equate that to 0. So when you multiply the main diagonal elements, you get lambda square, and then you have negative 2 pi over 3, and negative pi over 3 is negative pi lambda. And then you have 2 pi over 3 times pi over 3 is plus 2 pi square over 9. And then you subtract the other diagonal, minus. I have negative times negative is positive, so it stays minus 2 pi square over 9 again. And you equate that to 0. So of course, these two cancel. You factor out lambda, so you get lambda times lambda minus pi equals 0. So either lambda equals 0 or lambda equals pi. Okay, now you could have seen from the get-go is that you have two eigenvalues. Their sum is pi, because pi over 3 and 2 pi over 3 is pi. And their product is 0, because this minus that is 0. That determinant is, that matrix is singular. It doesn't have an inverse. Okay? So what are the two values that add up to pi and multiply to 0? There is nothing else other than 0 and pi. We know one of them is 0, so that the product is 0, but since they add up to pi, then the other is pi. So it's easy. Now we are going to say, what are the eigenvectors? So when lambda equals 0, you get pi over 3, negative pi over 3, and then again, negative 2 pi over 3 and 2 pi over 3. Of course, if you subtract twice, or if you add twice the top to the bottom becomes 0, 0. We know that these two equations, or these two rows are dependent. So we have a null space of 1, and basically when you multiply that by the vectors v1 and v2, you get 0. You only need one equation, so you get pi over 3 v1 minus pi over 3 v2 equals 0, meaning they are equal, right? Meaning if I divide by pi over 3 and add v2 to both sides, you get v1 equals v2. So I can write it as v or s or any number 1, 1. Excuse me. So that's the first eigenvector. The second one for lambda equals pi. Now, when you say pi over 3 minus pi is negative 2 pi over 3, negative pi over 3. And again, we don't need to do the next. It's the same. This minus pi is negative pi over 3. And again, two equations, but one of them is dependent. So you only have one equation, meaning you have to set one of the values to say constant and solve the other in terms of that constant. So we say negative 2 pi over 3 v1. And instead of saying minus, let's move it to the other side. And we say equals pi over 3 v2. And then I divide by pi over 3. So v2, you can write it as t times 1 negative 2. Because v2 is negative 2 v1. If v1 is 1, v2 would be negative 2. So these are the two eigenvectors. So now our original matrix can be written as follows. A can be written as pi over 3, negative pi over 3, negative 2 pi over 3. Oh, I'm sorry, what am I doing? That's the original matrix. Well, I didn't have to write it again, but okay. That can be written as 1, 1, 1, negative 2 times the eigenvalues being on the main diagonal, 0, pi, and 0, 0, times the inverse of that matrix. That matrix has a determinant of negative 2 minus 1 is negative 3. So after I solve, I divide by negative 3. I switch these two together. So I get negative 2 over negative 3 is 2/3. And the 1 will go here, divided by negative 3 is negative 1/3. The 1 and the 1, they don't change. They stay where they are. In this case, it doesn't matter if you switch them, they are the same, but we don't. Generally, we don't. We leave them as they are. We just change their sign. So the 1 and the 1 become negative 1 and negative 1. But remember, we are dividing by negative 3. So it becomes 1/3 and 1/3. And that's basically the matrix A written as P, D, P inverse. So now to get cosine of A, it's basically 1, 1, 1, negative 2. And then 0 and the pi, you take their cosine. Cosine of 0 is 1. Cosine of pi is negative 1, 0, 0, times 2/3, 1/3, 1/3, negative 1/3. So when I multiply these two, I get 1 plus 0 is 1. 0 plus negative 1 is negative 1. 1 times 1 is 1. And 0 plus 2 is 2. Times 2/3, 1/3, 1/3, negative 1/3 equals. Notice I multiply these two to get that, and now I multiply the product of these two by that. So you get 2/3 minus 1/3 is 1/3. 1/3 plus 1/3 is 2/3. 2/3 plus 2/3 is 4/3. And 1/3 minus 2/3 is negative 1/3. That matrix is cosine A. Suppose instead I was telling you find cosine square of A. Cosine square of A. Okay? If I had done that, then cosine 0 is 1, square is 1. Cosine pi is negative 1, but when you square it, it becomes positive 1. So basically, in that case, that would be the identity matrix, right? It would be 1, 0, 0, 1. So it's as if it's not there because that's like a 1 in multiplication. That leaves me with this matrix times that. But what is the product of these two? Notice this is P and this is P inverse. So cosine square of A would be the identity matrix, which is 1 in algebra. You say, wait a second, cosine square is 1? But doesn't Pythagoras theorem says sine square plus cosine square is 1? Does that mean sine square is 0? Yes, sir. Go back. If we were solving for sine instead of cosine, when we reach this stage, we would take sine of 0, which is 0. Sine of pi is 0, so you get the 0 matrix. And when you multiply anything by 0, you end up with 0. Isn't that interesting? Now, but wait a second. Are you telling me if I multiply this matrix by itself, I get the identity matrix? You should, unless I did something wrong in the math. Because this is cosine A, and we claim that this is cosine square of A. So let's check. I have 1/3, 4/3, 2/3, -1/3 times itself. So I get 1/9 plus 8/9, which is 1. Good. 2/9. Oh, I did something wrong. Oh, this is -1/3. I wrote it wrong. I'm sorry. So positive 2/9 minus 2/9 is 0. I caught myself before messing it up. 4/3 times 1/3 is 4/9 minus 4/9, so that's 0. And then 4 times 2 is 8/9. Negative times negative is positive 1/9 for a total of 1. Yes, sir. Cosine square of this matrix is 1. And sine square of this matrix is 0. Interesting, right? Okay, so that's the first example. The second example I wanted to do is a 3x3 matrix. And that matrix is basically matrix A here is 4, 6, 0, -3, -5, 0, -3, -6, 1. And I want to find the matrix E to the A. So I want to exponentiate that. Okay. We are going to do the same thing. We need to find the eigenvalues and the eigenvectors and proceed as usual. Now, remember what we did? We said that the sum of the eigenvalues, so lambda 1 plus lambda 2 plus lambda 3 should equal the sum of that which is 0. 4 minus the sum of the trace. 4 minus 5 is -1 plus 1 is 0. So they add up to 0. Excuse me. So either all three are zeros or 1 or 2 are positive and the other is negative, right? But what is the determinant of this matrix? Notice that if you expand the third column, this entry is positive, so only you multiply 1 by its minor. 1 times the 2 by 2 determinant, which is -20 minus -18. So -20 plus 18 is -2. So 3 numbers. Then when you multiply them, you get -2. And when you add them, you get 0. If you said 1, 1, and -2, you would be right. There is nothing else, right? If you change any number out of 1, 1, and -2, you will never get 0 as a sum and -2 as a product, but let's do it. So we are going to say that the determinant 4 minus lambda, 6, 0, -3, -5 minus lambda 0, -3, -6, 1 minus lambda equals 0. Again, I'm going to expand the third column. So I'm going to say 1 minus lambda times. And then again, I multiply these two minus those two. I get lambda square plus 5 minus 4, so plus lambda, minus 20 plus 18 minus 2 equals 0. This can be factored as lambda plus 2 times lambda minus 1 equals 0. So lambda 1 equals 1, lambda 2 equals 1 also, and for example, lambda 3 is -2. The order is not important. You can put them in any order you want, but you keep track which row, which identity or which eigenvalue goes with which eigenvector. Okay, so now let's say for lambda equals 1, that's interesting because if I make lambda equals 1, the first row becomes 3, 6, 0. The second one is -3. And when you subtract 1, you get -6, 0, which is identical to the first. And the third one will be -3, -6, 0. Wait a second. Wow. What is that? Meaning, if I add the second to the first and the third to the first, you'll get 3, 6, 0, 0, 0, 0, 0, 0, 0. So you have two dependent variables, meaning this is the null space would be 2. Since the V3 doesn't show up every time you would multiply it by 0, so one of the eigenvectors you can assume, let's make V3 equals S. Okay, so now I can say that that null space would be S times, you make V3 1. You can make it any number, but the easiest is 1. Notice it doesn't matter. Some people say, okay, what if I make this 2? It doesn't matter because that would change the magnitude of the determinant. So when you get the inverse of that matrix, it would be, the value would be half of it. So when you multiply them, they go back to 1. It doesn't matter. I can make that 100. Okay. And since 3 is multiplied by V1 and 6 is multiplied by V2, I would say 0 and 0. So that's one random, I was going to say one random variable. Okay, one eigenvector. The second eigenvector is that I'm going to say, okay, I have 3V1 plus 6V2 plus 0V3 equals 0. So here the V3 doesn't matter. But V1 and V2, if I divide by 3, I can get V1 equals -2V2. So if I call one of them T, it would be, if V2 is 1, then V1 would be -2. And in that case, I get the second one. Finally, I would say for lambda equals -2. 4 minus 2 is 2. 6, 0. -3. -3. Wait a second. Did that? This is 6. 4 minus -2. -3, -3, 0. And this one is -3, -6, -3. No, that's 1. Again, I subtracted 2 instead of -2. I'm sorry. So So 1 plus 2 is 1 plus 2 is 3. Why did I say negative in the beginning? Okay, times V1, V2, V3 equals 0, 0, 0. Say I have one equation dependent on the other. So from the first, so I say 6V1 plus, so I can say equals negative 6V2, right? Meaning V1 equals negative V2. But how about V3? If I write the third equation, I get negative 3V1 minus 6V2, but we saw that minus 6V2 is 6V1. So I can write it as plus 6V1 plus 3V3 equals 0, which means 3V1 plus 3V3 equals 0, meaning V1 equals negative V3 or V3 equals negative V1. So basically that guy, we said V1 is the negative of V3 and in the negative of V2 and the negative of V3. So I can write it as negative 1, 1, 1 or 1, negative 1, negative 1. It really doesn't matter. And here are the three eigenvectors. Okay? So now let's pick maybe the back of the first page. And represent the matrix A as first I enter the 0, 0, 1, negative 2. Here they are. Negative 2, 1, 0, and negative 1, 1, 1 times here the diagonal would be the eigenvalues 1, 1, negative 2. But to save time, I can say e to the A is e to the 1, e to the 1, e to the negative 2, right? And the rest are zeros, just to save time. Instead of writing A and then take the exponent of that. And then I want to take the inverse of this matrix. Again, this matrix, if you take its determinant, you can expand the first column. You have 0, 0. So you multiply 1 by its determinant. And the determinant is negative 2 plus 1 is negative 1. So you know what? I can say negative outside so that it's easy if I assume that the determinant is 1. It's much easier, right? Okay. Remember how to find the inverse of a 3 by 3 matrix? If the determinant is 1 or negative 1, in this case, we really don't care. But how do we find it? If you remember, I went over that in the engineering statics course when we were doing some linear algebra there. The first thing you see, it's a 3 by 3, so you would do positive, negative, positive, negative, positive, negative, positive, negative. What is that? Once you find the minor of each of these entries, you are going to multiply the elements, this diamond. So these elements by negative 1, you change their sign, and then you transpose. So if you are familiar with that, we can do it quickly. For example, I will start with this cross because they are all positive. The minor of that is 1 minus 0, so it's 1. The minor of this is 0 minus negative 1, so it's also 1. And the minor of that is 0 minus 0, so it's 0. And for these three, they stay the same. Why? Because the transpose of the main diagonal is the same, because this element is 1, 1. When you switch them, they are still 1, 1. 2, 2 stays 2, 2. 3, 3 stays 3, 3. So we don't have a problem here. Then I can take these two. I find the minor of that, but I write it here because I'm going to transpose. And the minor of that will be written there. So the minor of the 0 is 1. I'm sorry, I wanted this. The minor of the -1 is 0 minus 1. So it's -1, but I'm going to write it here. And the minor of that is -2 minus 1 is -1. I'm sorry, it's -2 plus 1 is -1. I'm going to write it here. And then for the remaining, after I find the minor and transpose, I will change their sign. Meaning the minor of the -2 here is 0 minus 1. So instead of -1, I would make it +1, and I'm going to write it here. The minor of this, I will change it and write it there. -2 minus 0 is -2, so I'm going to write it as +2 here. And finally, I want the minor of this to write it there after changing its sign. So I get 0 minus 0, it didn't matter. And the minor of that is 0 plus 2. So it's +2. I'm going to write it -2 here. But guess what? I have another negative sign outside, which will change all of those. So these would be, we can change them now with a different color. So we're going to say negative, negative, positive, negative, negative, positive, positive. And that basically, when I multiply these three matrices, I should get e to the a. So now this becomes positive also, since I already multiplied this matrix by -1. I know it's tedious, but what can we do? 0 plus 0 plus 0, that's 0. Then I multiply the first by the second. You get 0 minus 2e plus 0, so -2e. Then you multiply 0, 0, -e to the -2, -e to the -2. The second row, 0, 0, 0. Second row, second column, 0e, 0. Second row, third column, 0, 0, e to the -2. Third row, e, 0, 0, e. Third row, second column, 0, 0, 0. Third row, third column, 0, 0, e to the -2. And this would be multiplied by -1, -2, 1, -1, -1, 0, 1, 2, 0. First entry, 0, 2e minus e to the -2. That's the first element. Second, I get 0, 2e minus 2e to the -2. The third entry, first row, third column, 0 and 0 and 0. Okay? Now, what else do we have? Second row, 0, -e plus e to the -2. 0, -e again, plus 2e to the -2. And finally, e, 0, 0. So e. No, I entered e, 0, 0 here. I should take the second with the second, 0, 0, 0. That's 0. Third row, first column, -e plus 0 plus e to the -2, which is the same number as that. And last one is here, negative 2e plus 0 plus 2e to the negative 2. And this is e to the a. You may not be, you may not buy that, right? Let me first use my calculator to evaluate that. Of course, I'm not going to write it in like 2 decimal places or something. So let me see. 2e minus e to the negative 2. Oops, negative, not point. Negative 2. Error. Why? Oh, negative 2. I said negative 2 and I write minus 2 for some reason. 5.57. Okay, so I think with two decimal places, oh, it's minus, right? Why did I say plus? This is minus. So it's 5.3. 5.3. Okay. How about the second one? 2e oops, again plus, minus 2e to the negative 2, 5.17. The last one is 0, 0, and this is 2.71. If we use 2 decimal places, I have negative e. I will show you why I'm doing that. Negative 2.58, negative e plus 2e to the negative 2 is negative 2.45. And then the last negative e, yeah, it's the same, negative 258, right? Yeah, it's the same thing. So why am I repeating? This one is different. It's the opposite of that, right? I should get negative 517. I think it's, yeah. It's negative 2e. I don't know why am I doing it. Plus 2e to the negative 2. So it's negative 517. Now, how do I check my answer? You don't need to worry about that. I'm just saying, suppose I want to make sure that my numbers are correct. Somebody would say, I hear you. Take the natural log of that. You should get back what you had. Yes, but how can I find the eigenvalues and eigenvectors of this mess? Well, there are softwares. You can use something like MATLAB or some other software can do it. In fact, I think I found one calculator online. Eigenvector, eigenvalue calculator. Maybe that's Wolfram. Yeah, this one is easy. Okay, so now I'm going to use it to find, so I'm going to say here, make that 3. I'm going to enter these values. Of course, they are approximated, right? But we'll see. 5.3, 5.17. We'll see. I mean, I don't know. I want to make sure I didn't mess up. I was like not 100% sure of what I did here. So that would prove it. Again, as usual, 2.58, negative 2.45, and 0. and negative 2.58 and negative 5.17 and E. I should have see if I enter E, would it accept it? I never checked that. To give me error? No, it gave me E. Okay, so these are the eigenvalues and those are the eigenvectors. Of course, they approximate it. So I'm going to, for example, if I going to say the natural log of e to the a, which should give me a, would be the following. It would be the eigenvectors, which are the first one is, notice that this is 2, negative 2. Why? If you multiply 215 by 2, you get 516. And of course, because we are approximating, so that's negative 2, 1, 0. The second one, instead of E, I'm going to rewrite it. It should have been easier to write it 2.71. 2.71. Instead of doing the math, they will give us the... Okay, so negative 2, 1, 0. The second one is 0, 0, 1. And the third one is, you see, negative 1, 1, 1. These are just approximation. When you get 258 divided by 259, it's basically 1. Times. Well, the first lambda, notice I'm going to take the natural log of that. So I'm going to say natural log of 68 over 25, I get 1. That's E. The second, 2.7, so that's also E, because if you say second, no, I don't want second. I want the natural log of 2.71, right? 271 over 100. You get 0.9967. So the second one is also 1. And the third one is 13 over 100. Natural log of 0.13 is negative 2. The same eigenvalues we had before, 1, 1, and negative 2. And if I multiply that by the inverse of this, I expect to get back my original matrix. So let's see if that happens. That would be great. It means after all this confusion, it turns out to be correct. Hopefully, I will keep my fingers crossed. How do I find the inverse of that? I can do it fast, or you can do it with a calculator. Calculator is easier, I think. So I'm going to say, okay, here is my matrix. I'm going to create a 3 by 3 matrix. I'm going to enter negative 2, 0, negative 1, 1, 0, 1, 0, 1, 1. Let's go to matrix A, invert it, much faster. Here's what you get. Negative 1, negative 1, 0. I just don't want to waste your time. It's not hard to invert it, but in fact, I'm going to multiply these matrices, these 3 matrices together. So this was the third one. So A inverse, okay? So let's call this B and this C, and that's A inverse. So when I go back, so I'm going to go to matrix and do matrix B, and I make it 3 by 3, negative 2, 0, 1. I'm sorry, negative 1. It's much faster than if we multiply it ourselves. 0, 1, 1. Okay. And then this, I call it C. And then we're going to multiply B times C times inverse of A. Okay, let's do C. Also 3 by 3. It's 1, 0, 0, 0, 1, 0, 0, 0, negative 2. And now let's multiply matrix B times matrix C times matrix A inverse. Oh my God. Somebody else come and press it. 4, 6, 0, negative 3, negative 5, 0, negative 3, negative 6, 1, which was our original matrix. So when we took the natural log of this, we got the matrix. So that's definitely is e to the a. Because some people, when they see numbers, say, how can you prove it's e to the a? You know, you may be making, you know, any numbers, making up some numbers. But you see here, we got it right. Okay, I'm glad it happened. Sorry for the length of this session. It was long, but I wanted to show you about the sine square and cosine square, and then wanted to show you that if we take the natural log of our answer, we get back the original matrix exactly, which really is something I like. Thank you very much. And again, if you have any questions, leave me a note in the note section. And I will get back to you in the comment section. I will get back to you as soon as I can. Thank you very much for your time and hope to see you soon. Bye.